All right. Welcome back to the third lecture and the third day of the summer school. I want to take this time and opportunity to say thank you to many people. First of all, the organizing people who organized this conference. It's until now an amazing experience, and I'm very, very grateful that I have this chance to speak here and also to attend. So thank you for the organizing committee. Also, thank you for Richard for paying my flights to come here. And well, of course, everything else. And also thank you for the amazing technical team. I saw the video today of the lectures and I was blown away. They're amazing. Thank you so much. And also regarding the presentations, I had a lot of help from Elena, who's sitting here in the middle, and also Richard. And I need to admit that this lecture is a little bit out of my comfort zone. So in the end, I will swim around a bit and maybe even ask a special guest to do some calculations for me. Yes. All right, I hope I didn't forget anybody. And also, of course, thank you to all of you for attending, for asking great questions, and for being super nice to hang out with. Okay, third lecture. We're almost done with the introduction to classical shadows. Today will be the mathematical part, the most heavy part. And we will talk about complexity bounds and how we are sure that we converged to the right value that we want to converge to. And just a little recap. So we started very easy with basic notations and Pauli measurements. I explained to you that quantum state tomography is not an option to estimate things that you want to estimate in the end. We looked at this mysterious measurement channel. We demystified that a bit, I hope, show that it's just a depolarizing channel with different depolarizing strengths. Doesn't matter what measurement ensemble we put in. Then we looked at the multi-qubit measurement channel, where you were very brave and stayed with me with these tedious calculations. We saw what a vector T design is, and then we looked at the classical shadow protocol yesterday, where we did not have time to code, but I hope that you got the gist from the video. And today we will look at these complexity bounds, and I hope that you can also, I will start slow and explain to them how they come from and for which cases you can use them. So maybe in your studies or research, you can apply some of these bounds to your problems. Again, there's this challenge that Richard and me posed, where if somebody does, all the calculations is a bit too much, right? But the calculations of the shadow protocol for a nonlinear function in rho, namely a quadratic function in rho, and then also does a little coding exercise with this nonlinear function in rho estimation protocol, then send this solution to us with a little CV and a motivational letter, and then we will decide on who we invite with all the travel expenses covered to Linz. And now the deadline is from today in 2 weeks. Okay, great. If you have any questions, please approach me or write me an email, or, I'm very open to discuss about that. Cool. And again, I have this pad, right? You probably also have that from yesterday, where I tried to now collect the material a little bit. I did not have time to upload these slides, but I will do this, and I will also probably just send them to the organizing committee so they can upload it to the website. Okay, let's dive right into it. Remember, this was the classical shadow protocol, where the protocol goes as following. We prepare our quantum state that we are interested in. We apply a layer of random rotations, or a measurement ensemble, and then we perform a projective measurement in the Z basis. And then we record this one tuple. This is one data tuple, one shadow, which can have potentially, in the local case, n many unitaries written in this tuple, and then n many bits, right, for every qubit. And then from that, we can construct our snapshot. And from this snapshot, we can calculate a lot of observables all at once. And naively, you would think the snapshot lives in a complex space, so it has 2 to the power of n times 2 to the power of n many entries, the snapshot itself. So writing that down is exponentially costly, right? But I showed you yesterday a trick that if you know your observables, you don't need to write down your snapshot. You can really treat them as a tool to write down your estimates, which are just scalars, or maybe small matrices. Good. And then I showed you this little video here where we saw that the values that we are estimating are somehow converging to the right value. But if you look at this fidelity estimation up there, for example, it went away a little bit. So when do we know that this really truly converged to the value that we want? And the answer is complexity bounds. So in a bit of a more mathematical way, what is a complexity bound in our case? We want to make sure that the probability that our estimated empirical value is that the absolute deviation from our empirical value from our expected value, if it's that the probability that this is bigger equals some epsilon, which is our upper bound of our absolute value, that this is smaller than some function of n, where n is the number we had to ask our quantum computer about giving us data, right? Again, so we want this value here, probability that this is bigger than epsilon, we want to be this a small number. We want this probability to be small. The probability that something bad happens should be small, okay? It's a bit confusing in the beginning, but I hope I made that clear. And complexity bounds are there to estimate this function of n. And there's no equal sign because that's very hard to calculate. It's an upper bound. So the probability it can be lower, but when we write this down, we can be sure that it will not be bigger than that. Good. So the next half an hour will be about these complexity bounds and what do they tell us. And I want to, in the beginning, give a little example with, again, numbers, like we did with the vector T design. And my example is one of the most easiest examples that I could think of, the biased coin. So my example will be our single shot, our single toss is just one coin toss. And the probability that we land on tails is p, and that we land on heads is 1 minus p. Then the expected value of this I will always call mu, so the true one. And in our case, this is p, right? Let me just quickly write that down. So our expected value of x hat is the same as the probability that we will land heads times, what did I call heads? I think I called it 1. I will call heads 1 and then plus the probability that it will land on the other side, other way around. Sure? Isn't tails 0 and heads 1? Okay, thank you. Okay, then this is heads 0 times 0, and then tail times 1. And then this probability I can read off here. It's 1 minus p times 0. Yeah, thank you. Plus p times 1. So this is p. Okay. Now, what will also be important for us is the variance of this random variable. So the variance is the same as the expected value of our random variable squared minus the expected value of our random variable and then this squared, right? And now this we know, this is p. So this whole thing is p squared. And now we need to calculate this. So this is, again, this probability x head equals heads. It's times 0 squared, okay, plus the probability of x head being tails times 1 squared. And as you can see, nothing changes here. 0 squared is 0 and 1 squared is 1. So this is just p. So then the variance is the same as p minus p squared. And this is p times 1 minus p. Okay. Took care of the variance. Now, I told you that we want to bound the probability that our empirical average is not far away from our true value. So we are not talking about single-shot estimators, but these multitosses, these multi-shot estimators. And there, it is important to notice that we can use the law of large numbers that states that if we do this and n goes to infinity, the distribution of our multitoss variable will have a Gaussian form, always. It doesn't matter with which distribution we started. It will always, in the end, the multi-shot estimator of our distribution of the single-shot one will always end up to be Gaussian. And I always like to think of it as if we have n equals 1, then our distribution can either be, well, we either get p or 1 minus p, so we get 1 bar somewhere. Then with n equals 2, we can have 2 bars somewhere. With n equals 3, we already have 3 bars that can somehow be spread, and so on. And if we now go to n to infinity, we have a lot of bars that will, well, somehow, this is n equals big. And then if we go to n equals infinity, or n to infinity, then we will see that this will spread like a Gaussian curve. Okay, so we will use the law of large numbers, but later. First of all, we will start with one of the easiest complexity bounds that I know of, and it is called Markov's inequality. So Markov's inequality tells us that the probability that our, in this case, single shot, but it can also be the x bar, is larger or equal than a number a, which has to be bigger 0, where I also assume that x hat is bigger 0, is always smaller equals the expected value divided by this number. And if we now use this, and so remember, we want to bound the deviation of our sum. If we now set x hat to be actually x bar, so 1 over n sum over t and x hat t many things. So I mean, this is just calling the random variable x hat, but we can also say, okay, this is now our x hat. Then we have the probability of this sum minus the expected value. So in this case, I will call it, no, sorry, this being bigger equals than a is lower bounded by the expected value of this sum, right? I will call this mu bar. And now we somehow hope that we get some dependency on n here, because as I told you before, I want a function on n. I want to know my n is how many times I have to ask, and then I want to rephrase this and say, okay, so n is bigger equal this, then I can say something about how much I deviate. But as you can see, this is a linear function in my something that is a sum, so I can actually pull everything out here. So this is now 1 over n sum over t x hat t, which is mu. And this is n times mu, so this is actually just mu over a, which doesn't really tell me anything. N kind of was, well, crossed away, and that's bad. I don't want that. I want to have something depending on n, right? So that's not good. Now I need to think. So first of all, I want to not look at this, but the deviation. But that doesn't matter. It's also a random variable. So if I write probability of 1 over, okay, let's call this mu bar minus mu. This is also a random variable, right? I want this to be smaller or equals a. Now this could be negative, so I need to put some absolute value bars around it. And then I could say, okay, this is now smaller or equal the expected value of, well, this random variable here, divided by a. But I will be honest, I don't know how to calculate this. The expected value of the absolute value of mu bar minus mu, I don't know. So what I can do is I can just square this, I can just square both sides here, square. And then I also need to make a square here. And then I also, do I need to make a square there? I don't know. Ah, yes. And here, like this. And the A2. Okay, I just square everything. And now this is something that I know. This is actually the definition of the variance. So this is the same as my variance of my random variable mu bar by a square. And now let's call a square epsilon square. No, let's call, no, something is off. I need this, no? I don't know, I did something wrong. Okay, yeah. In the end, I want the so-called Chebyshev inequality that we just derived a bit clumsily. So my absolute deviation, yeah, now I have to take the square root. No, you're right. I told you that this is not my area of expertise. Sorry. Like this. And then I set, and then I do, then I take the square root on both sides, and then I have I equal a, and then the square stays. Okay, good. Pew. And I want to call it epsilon. Okay, cool. Now, in this case, if we have our distribution, when we draw our samples from a distribution in an IID fashion, so independent, we have independent variables, then we can calculate that the variance of our multi-shot estimator is actually the variance of our single-shot estimator divided by n. So the more times we ask our coin, the tighter the variance of the multi-shot estimator will be. And just keep in mind, we did not use that this obeys the law of large numbers. And in our case, so we can plug this in. And then, no, I don't want to show that yet. I don't know my slides so well. So we can plug this in for our case, and then we can, instead of variance of mu, we just write variance of x hat, and then divided by n. And our variance of x hat, I told you before, is 1 minus p times p divided by n epsilon square. And now we achieved what I told you in the beginning, what we have to achieve. We need some dependence of n on the right-hand side. Okay, now what do we do with it? This is not yet a sample complexity bound. It does not tell us yet how do we need to choose n to be epsilon far away, but we are almost there, because we can now say, I want this probability here, right? This is an upper bound of our probability that something goes wrong. Nobody saw that. So we want the probability that something goes horribly wrong to be upper bounded by some function of n, and we see our function of n, it's 1 over n, so the bigger n, the smaller the probability, good, right? And here we even put in some numbers, and now Jadwiga, want that this probability here is smaller than some number, delta, and we call this delta our confidence, or more 1 minus delta is our confidence. I could, for example, say I want this to be lesser than 5%. So then delta would be 0.05. Or I want this event to happen less than 1%. This is something that I can set. I can set delta, but delta should be very, very small because, again, there's a probability that something bad happens. And now we can use this right-hand side here to solve for n, because I told you we want to solve something for n. So then I need to take times n divided by delta. So n is actually larger equal p1 minus p divided by delta epsilon square. Whew. Now we have our first sample complexity bound. Cool. And I just want to say two things here. This scales with epsilon square, right? So epsilon is our absolute deviation. Let's say I want it to be 0.01 or something. Then this is squared. So this is 0.01 squared, which is 0.0001, which is a very small number. So that's already like a bit uncomfortable, but okay. But here, this is linear in delta, which is bad because delta should be as small as possible. So this is, it's a bound, but it's not ideal. We did not use it. We can use the law of large numbers, but okay. And I also want to point out that this still holds for variables that are not independent. So this bound could be used for distributions where I don't have the independence, and it will still hold true, with the variance, of course, looking a bit different because you have the covariance and everything. Okay. So now we go to the next bound, namely the Höfting inequality. And that's a bit of a bigger jump because here we do use, to derive this inequality, we do use that we have a law of large numbers here. And I will not go into details. Probably we could ask Richard to give us the whole derivation on why Höfting works and in what cases it breaks, but I will not do that with you. But here you can see that on the left-hand side we have the same expression, but on the right-hand side we have an exponential. So it's an exponential that scales with minus n. And that's much, much better. Why is that better? If we now do the same thing as I did with this delta, so Höfting my probability that I'm epsilon far away is smaller or equal to exponential of minus n epsilon squared divided by c, right? Yeah. And now what is c? C tells us how far away our single shots are from the expected value, or C is it tells us how bounded our random variable is. So if we know that it's in this interval between A and B, then C is B minus A. Now we can do the same thing. We can say, okay, I want this to be smaller or equal my 1 minus confidence. And now we do the same trick. So we solve for n. So we only look at this side here. And we solve for n. I'm running out of space. Then, first of all, I can divide by 2. And then I have this exponential, so I can take the logarithm. So we have minus n epsilon square over c log of delta over 2. Now I can take both sides minus 1. That makes this minus vanish. It makes my inequality flip around, and then we can put in the log and turn around the fraction in this logarithm. So this then means that we are like this, log of 2 over delta. And then here I can solve for n again. So we have n is larger or equal log of 2 over delta. And then we have c divided by epsilon square. So this is the sample complexity that we can derive with Höfting. And it's much more powerful because we have the logarithm of delta. Well, 1 minus delta. And the logarithm is much more powerful than just a linear function. So that's very good. It does not scale that bad. And in our case, what is c? in our case? What is the deviation? Huh? Somebody said something. No. Ah, okay. 1? Somebody said 1. Yes, it's 1. So I can say that I have kind of my min of p or 1 minus p, right? It's either this and then my max, p1 minus p, and I can just make my life easy and I say whatever, it's between 1. Or c is always smaller or equal 1. Okay. So in our case, Höfting would scale like this. So it lost the ability to kind of capture our p, our variance calculation, but it's now logarithmic in 1 over n. And we can even get better by not using Höfting, but the next equality that becomes more complicated, namely the Bernstein inequality. And this incorporates not only the deviations or the boundedness of our random variable, but also the variance of our random variable. And we have 2 cases in this bound. So again, the probability that we are far away from epsilon is bounded by, we have the upper case, where our variance is dominating our distribution, meaning that we don't have big outliers that can screw up our tails. Then we can use this upper part here where the dependency is there of the variance. And then we have the lower part where we have actually the outliers are, or the magnitude of our distribution is dominating, meaning that we have a much worse bound in that sense, in this heavy tail case. So upshot is that we always want to be in the upper part because the lower part is very bad. It scales bad and it does not really help us in our argument. And then again, when we look up in this upper part, we can, again, I will not do that in the blackboard, derive our sample complexity that is now where the variance is incorporated, and we again have a log of 1 over delta scaling in there. And in our case, what we can use for classical shadows, this is actually the strongest bound that we can use. So again, the Markov was a bit, well, useless. It only used the mean, and we did not have a decay in n. Then we went to Chebyshev, where we used the variance. Then we have a decay in 1 over n and also 1 over delta. It's pretty weak. Höfting, we use the boundedness and also in the derivation the law of large numbers. And then we have a exponential scaling. And then with Bernstein, we can use the variance, boundedness, and the law of large number. And this is then the strongest bound that we in our case can use. Okay. Now, I told you that do you have questions in this topic? Yes or no questions? Yes. Why we should use the variance? It will help us in the end. It will be stronger. I mean, yeah, maybe I should do the example with the yeah. Yes. Well, we bound the variance because we need the variance in our sample complexity, and it will be a stronger bound than without. Okay. Okay. Another question? Oh, we do not. We use IIDness. Okay. I said something wrong. We don't need the law of large numbers. Sorry. Should have. Yeah. I'm sorry. Good. Another question? Yeah. yes, we need to define the interval. If that's infinite, then, well, we cannot define C. Well, it's infinite, and then this doesn't work anymore. Yeah. It needs to be a bounded variable. A and B needs to be defined in some way. Yes. More questions? No. Okay. Now I told you that we not only want to look at one observable, estimate one observable, but a lot of them. And right now I only talked about one observable, like one of my estimation, one coin toss example. And luckily there's the union bound that tells us something about a lot of events that I want to bound. So if I have a union of many random events that I want to be sure that they're not more than epsilon far away, each one of them, then this is actually bounded by the sum of all these probabilities that we want to bound. And then we can just take a maximum over the sum. And then this is m times the maximum of, well, these probabilities that we are looking at. Okay? And you can see that m, the number of things I want to estimate, enters linearly in here, which is very good for us, because in the Bernstein inequality, we have an exponential bound. And if we now, I will just maybe quickly show you, or maybe it's clear. If we now do the same calculation as we did just with this right-hand side, then we will also take the logarithm of the number of things we want to estimate, m, which is convenient because m could be exponential in the number of qubits in our case. And exponential in the number of qubits means log of something to the power of n, where then we can pull out the n and it's linear in the number of qubits. So if we want to estimate exponentially many observables, then this enters linearly in this bound here. Okay, so that's very powerful. And it was one of the main results in the classical shadow paper that this is the case. And what I mean with the sigma, oh, there's a square missing, sigma square max is that I want to take the variance of the random variable that is maximizing this probability here. Okay. How am I on time? Good. Now, back to our classical shadow. Yes, one. Yeah. No, yes, exactly. It's not, well, I think it is. It is the largest variance because we, like, okay, let's maybe go through the equation. So we have max the probability that this is bigger equal epsilon. And now this we always wrote as 2 divided by 3/8, right? I think this is the Bernstein sigma square. And now this max here, we can pull in max 1 by m. Now this maximum over m, so this is actually now indexed by my I. We can pull this maximum inside the exponent and then pull it into the expression here. So I do think that the maximum of this probability is determined by the maximum of my variance. Yeah. Okay, coming back to our classical shadows. My turf again. So now we saw that we can bound our estimates with the Bernstein inequality if we know the variance of our estimation. And just to remind you, we looked at our measurement channels and everything, and then with the inverse, we defined these snapshots here, and they will be crucial to calculate our variances. And they also are different for the local and the global Clifford measurements. And we will start with the single qubit example and calculate the variance of the single qubit example, even though this is a bit of a boring task because, well, if I want to estimate observables of a single qubit, then, well, maybe just use quantum state tomography and everything is a bit easier, but this is just for the sake of showing the argument. So what we need to do for Bernstein is, first we need to calculate the upper bound of the variance of our estimator. Then we need to calculate the upper bound of our magnitude, R, how far are we away from our, how far away is each single shot from the true value or the maximum over that. And then we need to look at this fraction, which bounds epsilon, which then tells us that we can use this upper part of the Bernstein inequality for epsilon smaller than this fraction. And then we can just write down the sample complexity, which tells us, okay, with this and this many samples, you are sure that you're only epsilon far away with a confidence of 1 minus delta. Okay. So let's start for the single qubit observable estimation. Let's do the variance calculation. And just to remind you, our single shot estimator is this trace of O rho hat. And oops. So we need to calculate the variance of this property here. And we need to calculate this magnitude. So how far away are my single shots from the true value, which will then be upper bounded by some R, and this we will always call sigma square. So these two things we need to now calculate. Let's start with this one, the variance of our observable estimation. And as you probably know, this is always trace of O rho hat squared minus expected value of trace of O rho hat, this squared. And yesterday I told you that this is just trace of O rho, our true value. So I will not put much thought into that. This is just my true value. We need to now look at this second moment. Okay, so let's do the second moment. Our expected value of trace of O rho hat squared is the same as 1 over 3 sum over my unitaries in this unitary ensemble measurement ensemble. So this is 1 H as dagger, right? And then we have our bits, which can be 0 or 1. Then we have our Born probability, BU times rho. And now, yesterday and the day before, we always looked at operators, but now we look at numbers. So this is our number. And we have this thing on the right. Okay, good. So, maybe I should wait. I should go a step back and show you that this is not the only way we can calculate this. Because what we have in the right, so this trace O rho hat is actually trace of O, and then our rho hat is defined as the inverse of my measurement channel acting on U dagger B B U. Right, this is how we defined our snapshot. So I just inserted the definition of what our snapshot is in here. And you can see that this is our measurement channel acting on an operator on the right. And we will derive now that our measurement channel is actually a self-adjoint channel, meaning this will be the same as trace of m-1 O acting on our observable times U dagger B B U. So if this is the case, and I told you yesterday that I will always look at traces observables because we can just always get rid of the trace, then this would just be 3 times O, if this is the case here. So I first want to show you how that the measurement channel is self-adjoint. So let's just remember what the measurement channel is about. I will go to the right side for that. So we want to show that trace of, let's start with the measurement channel itself, of A, B is the same as trace of A, M acting on B. If we show this, then it's easy to do the same for the inverse. So let's start with the right-hand side. This is the same as 1/3. And now you're probably getting tired of this equation. I'm getting tired a bit about this U dagger B B U acting on A times U dagger B B U. So this is this part here, and then times B. And now this is linear, right? So we could pull this out, and then this trace only acts on this part here. So this is the same as trace S of 1/3. How do I want to do that? I want to pull it out. Third sum U and B. Trace of U dagger B B U A. And now this trace I will pull in here. Trace of U dagger B B U capital B. And now I can just rearrange everything and pull this trace out like this. So then this would be, let's also, pull this. So I will now pull this kind of here, and then this also here, right? I can just, everything is linear. So then we have trace of 1/3 my sum. Then we have, this is a number, I want to pull it in front. Trace of U dagger B B U times capital B. And then this is my operator now because of this trace here. So then we have U dagger B B and then A U A. And now this looks very familiar. Now we just need to make sure that A. So now this is our measurement channel acting on B, which is on the left side now, but that doesn't matter because the trace is cyclic. So we can really just pull A in front of here. And then we have shown that acting with the measurement channel on A is the same as acting with the measurement channel on B. So we have shown that it's self-adjoint. And now you're like, okay, but here we're looking at the inverse of the measurement channel, not just the measurement channel. And now we can do a little trick. We can just send A to the inverse of A, and then B being the inverse of B. So then we have trace of M acting on M inverse A times this acting on B. Okay, which is on the one hand, this cancels out, so this is just A m minus 1B. One way of seeing that. And we just showed that M is self-adjoint, so we can just, whoops, swap this to the right side. And then we also see that this is the same as M minus 1A. And then M minus 1 cancels B. Pew. So we have shown that the measurement channel's inverse is also self-adjoint. Top. So then this makes our life a bit easier. Because this value here, I mean, first of all, we know that this is the depolarizing channel with strength 3, acting on our O, which is the same as 3O minus, can you see? It's a bit up there, no? Maybe I write it down. Okay, so this is the same as D3 of O, which is 3 times O minus trace of O times identity divided by 2. But I just in the beginning said, we only have to care about traceless observables, so this is 0. So in the end, we only get 3 times O out here. Instead of still having this identity term flying around, that makes our life much easier. So instead of writing this, which is m minus 1 of Jadwiga B U squared, we can write this m minus 1 on O. And this we can write as 3O. Okay, this looks a bit easier. Now I want to pull out the 3 squared. And then I want to do the same trick as we did before. But now we actually have a trace of this thing, so we don't need to take partial traces. We can only say that this is now, well, 3 squared trace of O Jadwiga B U times itself. O Jadwiga B U. And it times the product of 2 traces is the trace of its tensor products. So I can just write this. Oop. And now this I can pull in here because we can do the same argument. And I think it's more neat if we think about that our observables are on the right here, because the trace is cyclic, we could have done that before. So this evaluates to, well, we have 3 squared divided by 3, our sum. And then we have trace of this. We have now 3 times 1, 2, 3. And I think I want to pull in the sum. And I want to also pull in the 1 over 3, or let me restart. We have this trace of sum of U and B. And then Jadwiga B U. And now to the tensor product of 3, not 2 as yesterday. And then we have rho tensor O tensor O. Okay, and now again, same argument as yesterday. We can look at this sum here. And I told you also yesterday that this not only forms a 2 design, but it also forms a 3 design. And the equation that we can use now is the same equation as we used yesterday. Okay, let's see if I know it by heart. So we have our definition of our vector T design. We have the average over all of our vectors, and then U dagger B U tensor T, and this is the same as D plus T minus 1 over T, the inverse of this binomial coefficient, over 1 over T factorial, and then we have all of our permutation on these T spaces that we look at. So for our case, T is equals to 3. Our V is 6, right? We have our 3 unitaries and then 2 vectors. And this part here, we also need to calculate now. So we have D plus 3 minus 1 is D plus 2 over 3 minus 1 over 3 factorial. Right. D plus 3 minus 1, yeah, D plus T over 2 over 3. And then this is our, again, N over K is the same as N factorial over N over K, N factorial over N minus K factorial K factorial. So in this case, we have D plus 2 divided by D plus 2 minus 3, so D minus 1, and then 3 factorial. And now we can do the same argument as yesterday, because this is actually D plus 2 times D plus 1 times D times D minus 1 factorial, and this cancels away. Also, when we take the inverse, this cancels away. So we are left with 1 over D plus 2, and then D plus 1, and then D. So this is our prefactor. And now we need to look at this sum here, because it's a 3 design, and we have more permutations than yesterday. We have 1 over 6 permutations in this case. So this looks a bit harder to solve than yesterday, right? But I can tell you that it's not that much harder. So let's maybe plug this in. So we have 1 over 6, and then we have this sum here. It's the same as 1 over, and now in our case, D is equals to 2. So we can just write 4 times 3 times 2, 4 times 3 times 2. This 2 cancels with this 2 times 3, and then we are left with 1 over 3. This equals this prefactor, and then all of our permutations in the S3 group. Swap over pi. Sorry. And that's convenient. There's a 1 over 3, and we also have a 1 over 3 here. So we really just need to plug in this calculation. So this is now the same as 3 squared trace off. Now we insert our 1 over 4 times 3 pi in S3 swap pi. This is a sum with 6 terms, and then acting on row tensor O tensor O. Okay, that's a bit S3. Okay, so what is this beast here now? And I want to use my beloved tensor diagrams because they come in very handy here. Okay, and the pi, I always think of all the collections of permutations, and I think the most understandable way how to write them is as we have our 3 spaces here. So we map from this space into, for example, this space. So 1 gets mapped to 1, 2 to 2, and 2 to 3. And in our tensor network language, we have 1, 2, 3 of these legs here. And then we have our space that we map into. And this just means we connect 1 with 1, 2 with 2, and 3 with 3. And this we can do with all the permutations now. So another permutation would be we map from 1 to 3, 2, we swap the first 2 spaces. So this would be, I need to do a bit of space management here. So 1, 2, 3. This gets mapped to 2. This gets mapped to 1, and this gets mapped to 3. And now we draw all of these spaghetti thingies, and I will drop the first line because I'm lazy. So now another permutation would be 1, 3, 2. So we swap the second ones, and you guessed it, it leaves the first one independent, and then it swaps these 2. Do I have space for 3 more? Yes. So now we swap them, and now we can swap the outer ones. This would be 3, 2, 1. Just means we swap these here, and then this stays invariant. And now we have the cyclic permutations. So we start with 1, 2, 3, and we just bloop, go around. So 3, 1, 2 would be 1. So 1 gets mapped to 3. 2 gets mapped to 1, and then 3 gets mapped to 2. And then last but not least, the other cyclic. So if we would now also take this and put the 2 here, we have 2, 3, 1. Is this correct? I think so. Then we would have 2, 3, 1. So 1 gets mapped to 2, 2 gets mapped to 3, and 3 gets mapped to 1. Okay? Okay. So these are the 3 terms in our sum here. And we see that they act on row tensor O, tensor O. So in these 3 terms here, we can literally, on the right, insert here a row, here O, and here an O. So we do this now everywhere. Row, O, O, row, O, O, row, O, O, row, O, O, and row, O, O. And now we take the trace over this object. And we take the trace over all 3 subspaces, meaning that we need to connect all the 3, well, now it looks like a vector, no? These are operators. Loop, loop, loop. And now we just need to connect all the open legs that stick out in the same plane. So in this case, we have 3 traces. And now it comes in handy that trace of O is equal to 0. So we have trace of row times trace of O times trace of O. This is 0. Good. So every time we connect a leg around an O, it will be 0. So here I already see this object here. Even though the first object, I can just take the row and swap it around here. This would be trace O row. The second object is trace of O. So this is also 0. Let's do that here. We have trace of row times trace of, and now the O we can shift into the other O, and this is trace of O squared, which is not 0. And then we do the same here. And here we again have a loop around O, so this is 0. And here we have a bit of a spaghetti entangled diagram, but I can see that there are no closed loops around an O, but we can always shift everything next to each other. So this would be trace of rho O squared, and the same is happening here. Everything is connected. So this is trace of rho O squared. So in summary, this term up there is actually trace of rho, trace of O squared, and then plus 2 times trace of rho O squared. That's a fairly easy expression for such a complicated expression up there. And we already know that trace of rho is always 1. Good. No space again. So, do I want to do that here? No, I want to insert it. So then the expected value of trace of O rho hat square is equals to 3 square. Then we have 1 over 4 times 3. And then we have trace of O square. And then plus 2 trace of rho O square. Okay. This looks good. This looks much easier than expected. But it's still dependent on rho. We do not want a dependency in rho in our variance calculation. So we need to get rid of it. And now we can upper bound this expression here, because I know that my I want to calculate the maximum of all quantum states over this expression here. And because of our properties of our quantum states, so we know that the largest eigenvalue can only be 1. We know that this is actually upper bounded by the spectral norm of the square of our operator, because this can at maximum give us the largest eigenvalue of this O squared. Okay, and because of some inequalities, I think it was the Hölder inequality or something, we also know that this is actually strictly, this is smaller than trace of O squared, which is the Frobenius norm. That's good, because we already have this trace of O squared, so we can now upper bound this with, now I can take this away and this away, 3 over 4. Did I mess up something? I don't know. 3 over 4, and then we have 3 times trace of O squared. Yes, and this, we can actually say that this is now smaller equal 3 trace of O squared. I can just, if I make this smaller, this gets bigger, right? So then I can just cross 1 3 away. So this now is our final variance of the single shot estimator of our linear function in rho. And this is also the variance that we will see in the classical shadow paper as stated. Good. So we did it. We calculated our first variance. Which is, well, 3 trace of O squared, so it depends on the observable that we look at. And what is this O squared? This O squared, so we know that we can have different observables, and if we, for example, want to estimate a fidelity, which is just a description of a quantum state, then we know that trace of this pure quantum state is always 1. So fidelity, we don't care about that, but if this would be, for example, a Pauli observable, so let's say x square is identity, and trace of identity is 2, so this would give us a number of 2. So for an observable that is a Pauli kind, this would be actually 2, this would be 6. Okay, just to give you some feeling for that. Now we need to look at this magnitude, or this r, so how far away am I from the expected value in the single shot regime. Are there any questions with this calculation? No. Okay. Oops. So we want to calculate R. And we start by looking at our single shot variable minus our expected variable. And in our case, this is trace of O row hat minus trace of O row. This looks a bit, well, I don't know how to handle that. This could be negative or positive, so I don't know if I can just drop this. I can just use the triangle inequality, which tells me that I can look at this value here. And this we just had because of the self-adjointness of our measurement channel. This is the same as, well, O m minus 1 on U dagger B U. Yes, plus trace of our row. So we can just act with our inverse on O, and we just saw that this is just 3 times O U dagger B U plus trace of O row. And here on this part, I can pull out the 3. And then this looks like 3 trace of, and now I want to use the cyclicity of the trace and actually look at B U dagger B U O U B. So I shift this around, I pull out the 3, so O is now sandwiched by these U's. And here I can make the same argument as before. This is a rank 1 projector that cuts out, in the worst case, the largest eigenvalue of my observable. So this is now 3, the spectral norm, so largest absolute value of my eigenvalue of O. And then this I can again have the same argument. Rho rank 1 could be rank, or is in the worst case a rank 1 projector that gets us the worst spectral value of our observable. And now this I can, again, as before, I mean, this is a much worse bound, but I could say that this is the same as upper bounded by for a trace of O square, the Frobenius norm. Okay, so this is R, which we need for our Bernstein inequality to check if we're in the right regime. Bloop. No. So this is our R. And now I told you that we need to look at the fraction of that to see if we can, well, to know the epsilon for which we can use the upper part of this Bernstein inequality. And we see that our epsilon has to be smaller than 3/4. That is very reasonable. So every time when I want my absolute deviation to be smaller than this number, I can use the sample complexity bound that I showed you, the Bernstein inequality, and inserting our variance upper bound into this equation now gives us this variance bound. Good. So it scales like 8 times trace of O square, and again, O square can be 1, trace of O square can be 1 for something like fidelity, or it can be 2 for something like a Pauli observable. Any questions? No. Okay, now, I think I don't have so much time anymore. Yeah. So we can say that for one observable, if our epsilon is in this interval, then the sample complexity holds. And now we can use the union bound from before and say that for m many observables, the same sample complexity holds, where we need to maximize now, like we need to find the observable that maximizes this probability, the single probabilities, and then just take this log m, so how many observables we want to look at. And that's also the bound that you will find in the classical shadow paper. Good. Now we go to the global case, and I think I don't have so much time anymore, so I cannot walk you through the whole derivation, but the upshot is that we look at the same estimation protocol here, but instead of 1/3, we would have 1 over my global Clifford group. Then my unitaries would be inside the global Clifford group with everything with n. The rest would stay untouched. The measurement channel is still self-adjoint, and so on. And then these swap operators here now act on 2 to the power of n big spaces. So we could do the same calculation, where we just need to keep track of n many of these legs here. But it's the same argument that holds here, because the swap operator would just swap everything at once, you know? Like it would swap this down here, and then if we would have one leg, this up here, and then we still loop everything together. So the argument is still the same. We just need to be a bit more careful what we swap around. And then in the end, the no dimensionality factor will enter here. And we still have the same bound, namely 3 trace of O squared, which for me was very surprising when I saw that. There's no dependency of n. Well, it's in the observable, but outside there's no dependency of n. Everything will cross away very nicely. I mean, we will have this be dependent on the dimension, but this will again cancel out and everything. So this is not, like, we will see the same thing here. And this is very surprising for me. So if we would do now this R calculation, so we would do this calculation now. We don't have this 3, but we have a 2n. So this here is 2n plus 1 instead of 3. And then we would pull this out and we would make the same argument. So in the end, we see that R scales exponentially with n. And this means that in our estimation protocol, our variance can be very, very tight. But I have, with a non-zero probability, some outliers that are exponentially far away from my center. And if I'm unlucky and in my estimation protocol, I hit one of these exponentially far away samples, then there's no way that I can recover with the samples that give me the mean. There's no way that I can in time recover from this one huge outlier. So in this case, if we would pull through this calculation, then epsilon, only if epsilon is exponentially small in the number of qubits, then we could write down this sample complexity. But that's not feasible. Epsilon is exponentially smaller than n, and you know how fast this grows to 0. So only when I want to estimate something to the, I don't know, 10 to the power of minus 20th digit, I can use this bound, but I lost already because 10 to the minus of 20, 10 to the minus of 20 to the power of 2 is a number that I can't even write down. It's so small. So we will not be able to use this argumentation for the global measurement ensemble. That sucks a bit, no? But, and now this is one of the biggest results of the classical shadow protocol. There's a trick how we can circumvent this disaster of a bound, and it's called median of means. So instead of saying my single shot estimator is just one shot for my probability distribution, I take n many shots of that, and then I take k patches. Now I don't remember which way around the variables are defined, but instead of one, I take k many. I calculate the mean of this. No, the median. Median of mean. Oh no, the median. I calculate the median of this, and this probability. This is an outlier is super small. And then with this, I can write down a new sample complexity bound that does not scale, where my epsilon does not scale in exponentially in n anymore. So upshot, this median of means is only necessary if you need to take care of outliers in your probability distribution. Else it is not necessary, else it will even harm your estimation protocol. If you have more questions, you can ask Richard about it. I'm just telling you what he told me, actually. Okay. I think one time a student asked me about this median of means. I hope that this answered the question. So this is now for the global case. We fixed that one with a small trick. Well, they fixed that one with a small, aka huge trick. And now we can look at the local observable, local observable estimation. And I will be very honest and frank with you. I did not have the time to do the calculation myself. Hence, I will not show you the calculation. But the upshot of this is, and we only have 10 minutes left. So my joker would have been Richard, who could have told us how we can do this calculation, but I will need to refrain from that. But the upshot of this local observable estimation is that our variance only scales with the number of localities, so k, which is good because when we look at, for example, we have 100 qubits, and our k is just 2 or 3, so we only look at 2 local observables. An example would be maybe some Hamiltonian that only has local interactions, and then want to estimate the ground state of this Hamiltonian. Then my k is very small compared to the number of qubits, and luckily our variance only scales with the number of locality. So we can just ramp up our lattice of qubits. It will not really harm our sample complexity. Okay, that's good news, no? Because normally we look at very local things as physicists, and I think a lot of people here are physicists, so classical shadows are very good in this regard. Okay, so with that, we have filled our table, finally, with the single qubit being just an extension of the multi-qubit one. And I added now the sample complexities for m many observables here. And I just want to make one remark. So here it's very good to look at local observables. And, oh, the square is wrong. And in this global Clifford measurement ensemble, we have no dependency on n, not direct dependency, but we have this trace of O squared. And trace of O squared can be tricky, because again, if we want to look at fidelities, for example, then trace of O squared is 1. Meaning that we ramp up the number of qubits and we do not scale in our sample complexity. We just need the same number of samples, which I find very remarkable. But if we now have trace of O squared of a Pauli, then this scales again exponential in n, right? Because we have a Pauli string, x tensor x, we square this, then we have identity 3 times, and the trace of that is 2 to the power of 3. So looking at that in the n qubit case, 2 to the power of n. So here it's important that we look at the right observable, and then the global Cliffords can really do a very good job for us. Okay, And with that, this is my last slide. I want to end this science session. And if you have any questions, please come to me or to Richard or to Elena. Thank you so much for your attention. One last thing. I want to advertise our group because Richard now has 3 positions for postdoc positions. And we would be super, super happy to have 1 or more postdocs that come to us to Linz. And as you can see, I'm a woman. I'm the only female speaker in this conference or in the summer school. And I'm very, very happy if we would get somebody who has a more diverse background than just the standard white cis male, which is not bad, yeah. But it would be amazing to have people as postdocs who maybe diversify our team a bit. So please reach out to me or to Richard if you are interested in the postdoc. We would be very happy to make it happen. And there are also still always some positions open for PhD students. So also approach us for that and come to us in Linz. All right. And with this, I will close the session. Thank you.